Because how do we describe speed? We describe speed as distance upon time. At a very simple level. Okay. So if we visualize the relationship between distance covered, okay, if we visualize the relationship between distance covered with respect to time, okay, we can see that such a motion, okay, which is a straight line motion, uniform motion along a straight line, the distance time graph, how would that one look like? That would look like this. Okay. So that's how we understand that it's covering equal distances in equal intervals of time. If we take any interval of time which is delta t, okay, the symbol used for an interval or for a change in a quantity is delta t, we will see that the distance traveled will be same. Okay. Why? Because the speed is uniform. Okay, so you can see that this angle is equal to this angle, which is equal to this angle. Okay. So in other words, if we look at the distance versus time graph, okay, because the speed is uniform, uniform speed implies that the distance time graph is a straight line.
What?
Okay, so then what happens is when we have this type of a graph, which is a straight line graph or what we call a linear function or a linear graph between distance and time, then we have another aspect over here, that if we define average speed versus instantaneous speed, okay, can anybody tell me what is the meaning of the term average speed?
The total distance upon total time.
Yes, very good. Okay, so average speed, so when we say average speed, okay, what is it defined for? Total distance upon total time, right? So it is defined for the total amount of time. So that means it is defined for an interval of time, right? So
Yes, sir.
average speed is equal to the total distance in a time interval divided by the total time for that interval. So that's why we, in symbolic language, we can write average speed as, let's say, delta S by delta T. Okay. Or we can write it as the distance traveled in the interval of time 1 to 2 divided by the time T2 minus T1. Well, let's say this time here is T1, this time here is T2. So this delta T is T2 minus T1. And this distance, delta S over here, is the distance traveled in the interval 1 to 2. Okay. Now, more interestingly, so coming back to this linear graph, okay, if the motion is uniform, then the interesting thing is that the average speed is the same for all intervals. Right? This statement is making sense that whatever interval of time we take, the average speed will be the same, because you can see that the slope is always the same for the straight line. Okay. So, if we have a graph of time varying according to 1 second, 2 seconds, 3 seconds, 4 seconds like this, and distance varying in meters, like let's say 10, 20, 30, whatever. Okay. Now we can see that whether we take the interval of 0 to 2 seconds, okay, or we take the interval of 2 to 3 seconds, okay, or we take the interval of 1 to 4 seconds, whatever we like, the ratio of distance traveled divided by the ratio of the divided by the time interval will be the same for all intervals. Okay. So in this example, you can see that here the average speed, for example, from 0 to 1 second is 10 meters divided by 1 second. So it is 10 meters per second. But if I calculate the average speed from, let's say, 3 to 4 seconds, again, then it's the same, because in 3 to 4 seconds, the total distance is going from 30 to 40. So it is again that much only. It is 10 meters divided by the time interval, which is 4 minus 3. So that is 1 second. So it is again 10 meters per second only. If we calculate the average speed, let's say between 2 to 4 seconds, then the total distance traveled between 2 and 4 seconds, you can see, is going. So at 2 seconds, the distance from the initial time 0 was 20 meters, and at 4 seconds, it was 40. So the distance is 40 minus 20, okay, divided by the time interval, which is 2 seconds. So again, you can see it is 10 meters per second. So what happens is, when we talk about average speed, okay, average speed is defined for, we'll come back to instantaneous speed later. Okay. Average speed is defined for an interval of time. But in the case of uniform motion, what happens that whatever interval of time that we select, the average speed is the same. Okay. So average speed, it is defined for a time interval. Let's say delta t, which is some final time minus initial time. But in the case of uniform motion, it is same for all intervals. Okay. So that is about average speed in uniform straight line motion. Okay. Now let's talk about instantaneous speed. Now, what is instantaneous speed? Anybody has an answer for that? Can anybody describe what is instantaneous speed?
So
How
the
it is
change
different?
in speed upon change in time.
Change in speed upon change in time? Nahi beta. Think again.
It's a
Because what is the unit of speed?
speed of a particle at the given particular moment, at the very instant.
At the very instant. That's correct. Okay. So it is. So one way of describing instantaneous speed is, it is the speed at a particular instant. Okay, so let's try to understand now how we would measure such a thing. Speed at a particular instant. So what do we mean by this thing? That it is the speed at a particular instant, because average speed we had calculated as the ratio of distance with respect to time for a time interval. Okay. So yes, Adinath, your answer is correct. Okay. So how, for example, if we are doing a practical experiment, okay, and it's related to, let's say, a car moving at uniform speed along a straight line, so it has uniform motion. So, or forget about the car moving at uniform speed. Let's just say that we are in a car which is moving, okay, in a particular. It need not even be a straight line, etc. Okay, how would we calculate the instantaneous speed at a given? How would we measure the instantaneous speed? We would require a device called a speedometer, right?
Yes, sir.
Yes, sir.
So how now see, in general, unless a vehicle is moving at constant speed, the speedometer's value that it's showing, the reading that it is showing, that is continuously changing. from time to time, from instant to instant. Okay, so how does it actually measure? And what does the speedometer actually measure? Any idea about that?
Speed of the vehicle at a particular time.
That's fine. It measures instantaneous speed. Okay, but how does it exactly measure it? What quantity does it measure?
Number of wheel
rotation of wheels.
Yes, very good. It measures something called RPM, no? The number of rotations per minute, or it measures the rotational time. Okay, at that particular instant, it measures the angular speed of the wheel. That is the speed with which the wheel is rotating. So indirectly, it measures the time taken for a single rotation. Now you can imagine that compared to the full journey time, the time taken for a single rotation of the wheel of a vehicle is very, very small, right?
Yes.
Now in one rotation, can you tell me how much a wheel would tend to move? If we have a wheel,
1 meter.
okay, let me
Sorry,
rephrase my
okay.
question. If we have a wheel which is of radius r, okay, and of course this
2
wheel is
pi r.
doing a, yeah, is 2 pi r, is doing a motion which is called rolling. So imagine we have a point over here. Okay, now in one full rotation, so what the wheel does is it's in a motion, it's in a combination of what we call translation and rotation. It's moving like this also, and at the same time it's rotating about its own axis also. So this point, it describes actually this sort of a motion. Later in physics we will study that this is called a cycloidal motion. So as the wheel is going from point to point, that point A is here, then later it's here like this. Okay, so for example, if this line is AB, this line has become something like this now, and then by the time one full rotation is completed, it is back to this point here. Okay, so now if we just want to visualize how much distance the wheel has traveled in one full rotation, okay, want to just visualize that how much is, so this is when it is completed. If this was t equal to 0, this is, let's say, t equal to capital T, it is the time taken for one rotation. Then this distance traveled, it becomes 2 pi r. It makes sense why it becomes 2 pi r. Okay,
Yes, sir.
Yes,
yeah,
sir.
just imagine that the outer surface of this wheel or cylinder or whatever is lined with some paint, right? So what is the length of the paint that it will throw on the floor by the time it completes one rotation? Every point on this will come in contact at some point of time. Every point on the circumference from A right back to A will come in contact with the surface over here. So the length of this path, okay, or the length of the ink line that will show from here to here in one rotation will be equal to the length of the circumference, right? So that's why it will be equal to 2 pi r. So you can see that if we calculate the speed from 0 to capital T, okay, so that's basically the average speed from 0 to capital T is going to be 2 pi r divided by capital T, where capital T is what we call the time period of rotation. Okay, so now if your speedometer is able to measure this thing, okay, because it's measuring the rate at which the wheel is rotating, so it's measuring something called angular speed. Okay, so we'll come back to angular speed later, but just understand that through angular speed it is able to measure capital T. Okay, so if it's able to measure capital T, it can measure this quantity 2 pi r divided by T, because 2 pi r is a known quantity for the wheel. So in that case, what is happening is that it is measuring the distance traveled upon time, but comparatively for a very, very small interval of time. So that is what we mean by instantaneous speed. Okay, so instantaneous speed in that sense is again the rate of distance with respect to time, but for an extremely short amount of time. So we will give this kind of interval of time which is extremely short. We will give it a specific definition as we go along. Okay. So instantaneous speed is equal to delta S by delta T, but under the condition that delta T should be extremely short. Okay. So for example, one way of achieving this practically might be that we want to find for instantaneous speed at the instant, let's say t equal to 2 seconds for a given object which is moving. Okay, we might say that we want to calculate delta S by delta T, where delta T is an interval of time, like let's say 0.01 seconds. So it is, so delta S is equal to the distance traveled from t equal to, or you can say t1 equal to 2 seconds to t2 equal to 2.01 seconds. So that is my delta S. Okay. So we will become equal to that delta S divided by 0.01 seconds. Okay, so that's one way of saying that practically how I could achieve the calculation of instantaneous speed. But then if somebody else is doing the same calculation, okay, but they are taking delta T as 0.001 seconds, okay, then for them the instantaneous speed would be delta S would be the distance from t1 equal to 2.000 seconds to t2 equal to 2.001 second. Okay. So they would have, so let's say it's delta S prime. So they would have calculated the instantaneous speed as delta S prime divided by 0.001 second. So now if we compare this calculation with this calculation, this one with this one, we will see that this one is a more accurate calculation compared to this, because the interval of time taken is even shorter. So when we say that this is the definition of instantaneous speed, what we can say is that the shorter the interval of time, okay, the more accurate the measurement. Okay. So hope this point is clear to all of you. Now coming back to instantaneous speed of a uniform. Yeah, yes, Beta, tell me.
So do we have to write side by side, or you will give time to write?
I will give you some time to write, don't worry. Okay.
Okay, fine.
So the point is clear, na, so far?
Yes, sir.
Okay. So now if we talk about...
Sir, can you explain the last example once again?
Yes,
yeah.
sir.
Yeah. Okay. So in the last example, what I'm saying is that, let's say we want to calculate instantaneous speed for something which is moving. So instantaneous speed is always defined at a particular instant of time, right? That's how we've seen the definition. It is the speed at a particular instant. But how do we measure the speed at a particular instant? So practically what it becomes the rate of distance with respect to time for an extremely short interval of time. Right? This definition is clear, no?
Yes, sir.
Okay. Now let's apply it to this last example. So the last example, I'm saying that I want to calculate the instantaneous speed for a moving object at the instant of time t equal to 2 seconds. Okay, so what I'll have to do is I'll have to calculate distance upon time, but for a very, very short interval of time. All right. So let's say in my first case, I've taken that interval of time to be 0.01 seconds. So in that case, what should be the numerator delta S over here? It should be the distance traveled in that small interval of time of 0.01 seconds. So that means I'm calculating at the instant of 2 seconds. That means I should calculate the distance traveled in 2 seconds to 2.01 second. Understanding the point now?
Yes, sir.
Okay, because delta t that I have selected is 0.1 seconds in this case, okay, and I'm calculating v is the instantaneous speed at t equal to 2 seconds. So I should consider my interval of time delta t between t1, which is exactly 2 seconds, and t2, which is t1 plus delta t, or 2.01 seconds, right? And I should go ahead and calculate this ratio of delta s by delta t. So when I calculate this ratio of delta s by delta t, delta s will be this thing. It will be the distance traveled from t1 to t2. So that divided by the time interval of delta t, which is 0.1 seconds, will give me the measurement of the instantaneous speed. Right? This is clear?
Yes, sir.
Okay. Now let's say in a second case, I'm able to do this calculation for an even shorter interval of time, shorter by a factor of 1/10. So it's actually 1 millisecond, as you can see. This was 10 milliseconds. So I'm calculating the distance traveled divided by the time taken. But in this case, I'm taking the time taken as what? I'm taking delta t as 1 millisecond. So this will become the formula. After I measure the value of distance, I have to divide it by 1 millisecond. And that will give me the instantaneous speed at t equal to 2 seconds, right?
Yes, sir.
Okay. Now, if I compare the two measurements, what I can say about their accuracy? Comparing the two measurements, I can say that this one is more accurate. Does that make sense? Why it is more accurate? Because the interval of time I've taken in this case is shorter. No? So the smaller the interval of time, the better the accuracy of my measurement.
Right.
Okay. So that was the point of this example. Hope this is clear.
Sir.
Okay. Yeah. So Siddharth, you have asked the question, why shorter interval gives more accuracy? Okay. Because instantaneous speed is defined as speed at that particular instant. No? So the moment I'm taking an interval of time, okay, I'm defining that instant of time as between time t1 and t2. So as you know, a perfect instant of time has no interval. No? It is just at that moment. So the lesser the time interval between t1 and t2, the closer it is to a perfect instant. You understanding now? The instant of time means at a particular moment, right?
Yes, sir. Thanks.
Okay. Okay, now let's come back to the case of uniform motion. Okay. So uniform motion along a straight line. So what happens in the case of uniform motion along a straight line? We have already understood that the distance time graph is a straight line. So the straight line has a wonderful property that if you look at the ratio of distance versus time for any interval of time is the same. So we had seen that average speed was same for any interval of time. Now, what can we say about instantaneous speed? When we talk about average speed in a certain interval of time, let's say t1 to t2, it was equal to this distance divided by t2 minus t1. So average speed from t1 to t2 was equal to delta s divided by t2 minus t1. But now suppose I want to calculate instantaneous speed at this time. Let's say this time is some t prime. Now what about instantaneous speed at t equal to t prime? So practically to calculate instantaneous speed, what I'll have to do is I'll have to take a very, very small interval of time. Okay, so I'll have to magnify this graph many times, as many times as possible. Okay, so that I'm able to select a point which is very, very close to this. So I'll have to select a second point, which is, let's say, like this. Okay, so which is almost at the same time as t prime. So I'll have to select a time such that this interval over here is a very small delta t. It's extremely small. Okay, so accordingly, what will happen is during that very small interval of time, this quantity over here, delta s, will also become very small. Okay, but if I magnify this diagram many times, you will see that between this instant and this instant, if I magnified this many times, you will see that between these two instants, the slope is the same. The slope is very much the same. Okay, so the ratio of this delta s by delta t. So let's say I put this under magnifier. So now this is becoming the instantaneous speed. So this quantity that we were calculating, this is now this delta s by delta t, but under the condition that delta t is extremely small. Okay, but if this angle is theta, you can see that this is also equal to tan theta, or what we call slope of the straight line. And this thing, this angle will also be theta. Okay, because just like this triangle will have the same theta as any other triangle, so that extremely small triangle over there will also have the same theta. It will have the same inclination. So this will also be tan theta. So what we can then say about the uniform motion along a straight line? Instantaneous speed is equal to average speed is equal to delta s by delta t, which is nothing but slope of the distance time graph. Okay, which is a straight line graph for uniform motion.
So the instantaneous speed is equals to average speed only in the straight line graph, right?
Yes, so exactly, only in the case where the motion is uniform. So this is one of the important properties of straight line motion, of uniform motion. Okay, so this is an important
Can you explain the
property.
tan theta again?
This is a property of uniform motion. Yeah, I'll explain. Okay, let's come back to that tan theta thing. Okay, so we'll come back to this. Let's look at equation of straight line. Equation and graph of a straight line. Right. So equation of a straight line is given by the relation y is equal to mx plus c, where m is a constant which we call the slope, right? And c is a constant, the different constant, but it's constant, called the y-intercept. Okay. So if I draw a straight line graph which has positive values of m and c, for example, So for example, if I draw the graph of y is equal to 2x plus 3. So it's a straight line which has a slope of 2 and a y-intercept of plus 3. Okay. Then how that straight line will be looking? Okay, so we can plot different ordered pairs and we will come to the conclusion that it looks something like this. We plot different points. Now I'm just plotting it on the positive side of x. It will of course continue to the negative side also, but I'm not immediately concerned about that. Okay. So this point will be how much? It will be when x is 0, the value of y is 3. So it will be 0, 3. Okay. Now let's say x equal to 1 lies here, x equal to 2 lies here. So this point will correspond to the ordered pair. When x is equal to 1, you can see the value of y is becoming 5. Okay. When x is equal to 2, you can see the value of y is correspondingly becoming 7. Now, if you look at the trigonometry involved in this, you'll realize this point that y it is equal to tan theta. Or you take any general triangle which is formed by a base of x2 minus x1 and a corresponding perpendicular of y2 minus y1. Now these triangles are all similar. Whatever this angle theta, it is the inclination of this straight line with respect to the horizontal. Now, this line that I'm drawing, it's parallel to the x-axis. Is it clear? So same with this.
The equation is defined. The equation is defined for the graph.
Yes, equation is defined for the graph. So this angle is theta. So now you can see that any point that we take over here, which is x2, y2, and similarly any point here, which is x1, y1, it satisfies the equation that y2 is equal to m times x2 plus c. And that one satisfies the equation that y1 is equal to m times x1 plus c. So if you just subtract these two, you can see y2 minus y1 is equal to m times x2 minus x1. So in this particular case, y2 minus y1 is equal to, or this ratio is equal to 2. Okay. The slope of the straight line is nothing but change in y upon change in x. Okay. Now coming back to the graph, that is nothing but perpendicular upon base for all these triangles. So it is nothing but tan theta.
So can you explain it again from M?
From this point here?
From defining, no sir, before that. Like
This
you have taken M is equals to 2 and C is equals to 3.
Okay, so you're just comparing this with the standard equation of straight line. What is the standard equation of straight line? Y equal to mx plus c. So the coefficient of x is what we call the slope, m. And the independent constant is what we call the y-intercept c. So now compare this equation with this one. Got it now?
Yes, sir.
So y is equal to mx plus c. In this particular case, in this particular example, that is 2x plus 3. So what is the coefficient of x? It's 2. So m is equal to 2. Right? And what is the independent constant term? It's 3. So c is equal to 3. Is it clear now?
Yes, sir.
Okay. Now any particular point which lies on this straight line, it will satisfy the equation of the straight line. So if we have the equation y is equal to 2x plus 3. So for example, if we take x1 as 1, how will we calculate the value of y1? It will be 2 into 1 plus 3, no? So it will be 5. Okay. So how is x1 related to y1? Y1 is equal to m times x1 plus c. That is why this point had a y coordinate of 5 when it had an x coordinate of 1. Is this clear now?
Yes, sir.
Okay. So that's how we've got these two equations, that y2 is equal to m times x2 plus c. and y1 is equal to m times x1 plus c. So now algebraically, if we just subtract these two equations, what relation we'll get? That y2 minus y1 is m times x2 minus x1, or y2 minus y1 upon x2 minus x1 is slope. So this is the algebraic meaning of slope, that m is equal to the ratio of delta y by delta x, or y2 minus y1 upon x2 minus x1. So in this particular case, that m is equal to 2, right? So algebraic meaning of m is clear.
Yes, sir. And sir, how did we get this y is equals to mx plus c?
That is the equation of straight line, na beta? That is the general
Like,
equation of
it's
straight
not
line.
derived.
No, that is the definition of it. No, it's not derived from anything. It's the definition of the equation of straight line. For example, if I have an equation that y is equal to ax squared plus bx plus c, will it be a straight line? No, no, because it's got a square term. You
Yes,
understand?
sir.
So this will be the equation of a quadratic equation. Okay. This will be a quadratic curve. We will come back to this also. But this is the equation of a straight line. Okay. So this graph actually shows you that a straight line has this property that any 2 points that lie on it, x1, y1 and x2, y2, if we write the rate of change between those 2 points, that is y2 minus y1 upon x2 minus x1, regardless of what my x1 and x2 are, okay, the slope is the same, which is why the shape of this curve or the shape of this in coordinate geometry becomes a straight line, because theta is same for all these triangles. Is the point clear now?
Sure, sir.
Right, so this was the algebraic meaning, that m is equal to y2 minus y1 upon x2 minus x1. Now geometrically, what is the meaning of this? So you come back to this triangle. Yeah, Maitreyi, you have a doubt, beta?
No, sir.
Okay. So you come back to this triangle, any of these triangles, what is tan theta equal to? It is perpendicular upon base. So see, between these 2 points, x1, y1 and x2, y2, what is perpendicular upon base? It is y2 minus y1 divided by x2 minus x1. So the geometric meaning of slope, it becomes what? That m is equal to nothing but tan theta, or y2 minus y1 upon x2 minus x1 is equal to tan theta. Okay, so that is why we say that for an equation of straight line like this, the slope m is equal to the rate of change delta y by delta x. Okay, that is equal to tan theta. So in other words, we say that the slope equals to the rate of change of y with respect to x, which equals to tan theta, where theta is the angle of inclination of the straight line with respect to the x-axis. Okay, so this is part of the definition of straight line in coordinate geometry, something that I'm sure most of you have studied at 9th, 10th level. You are aware of this, right? Any doubt with this, please let me know first. Okay. So now when we apply this information to our uniform motion along a straight line. So what we observe about uniform motion along a straight line, that if we calculate distance versus time, is going to be a straight line graph passing through the origin. Why? Because obviously distance has to start from 0. So this is more like a straight line of this type, that distance is equal to some constant velocity or some constant speed into time. Now, so if it had been an XY graph, this is a graph of the particular type, straight line graph of the particular type, which is passing through this origin. So y is equal to mx, c is equal to 0. So what is the value of m? M is the slope, which is delta y by delta x, which is equal to tan theta. Okay. So the same thing now we are applying, where y is represented by distance and the x-axis is represented by time. So what it says, that the rate of change of distance with respect to time is uniform for all intervals. But not only it is uniform for all intervals, if I calculate this rate of change for a very, very small interval, that means I'm calculating instantaneous rate of change. So that instantaneous rate of change will also have the same value, which is the slope of the same straight line as the average rate of change between two different times, t1 and t2, or for an interval of time. So that is the property of uniform motion. Okay, that instantaneous speed, that is speed at a particular instant, will be equal to average speed for any interval during the motion. So the instantaneous speed at any instant will be equal to the average speed for any interval of time during the motion. And that is equal to basically what? That is the equal to the slope of the distance time graph. Okay, so hope this point is clear to all of you. Okay. So we've discussed about the relationship between instantaneous speed and average speed. And in particular, we have discussed why instantaneous speed is equal to average speed in the case of uniform motion, or in the case of motion with uniform speed along a straight line. Okay, so just I'll take you back to the beginning of the discussion. You can note down some of the key points. Just take a couple of minutes to note down any key points that you want. Okay, don't worry about calculus. We'll come back to that. You can start from this thing that Okay, so you don't have to make very detailed notes at this stage because, as you know, I'll be sending you the whiteboard notes. Later, when you're revising today's lecture, you can make more detailed notes. But just go through these points once and jot down the important aspects. And more importantly, as you're going through it, if you have any doubt with any of the points, just let me know. I'll explain that point again. Okay. So this is just some background information. Okay, we haven't started calculus in that sense yet, but this background information is important to understand calculus, okay, and understand the concept of instantaneous rate of change. So the practical example of this would be that, you know, if you have an object on a perfectly frictionless surface, okay, like imagine you have a carom board whose surface is very, very smooth, so there's no friction at all between the carom coins and the surface of the carom board, and you strike one of the coins. Okay. So before it makes a collision with anything else, it's moving along a straight line with uniform speed because there's no friction. So if you were to track the distance traveled by such an object moving on a frictionless surface with uniform speed, if you were to track the distance versus time, you would if you plot that data which you have tracked on a graph, your graph of distance versus time would look like this. It would look like a straight line. So that straight line of distance versus time represents what we call uniform motion because it happens when the speed along a straight line is constant. So that being the case, you can see that it has that very interesting unique property that whether I calculate the average speed between two instants of time, that is delta s by delta t, where delta t is t2 minus t1. So it's two distinct points of time, like I've shown on the graph, this time t1 and this time t2. Or I calculate the instantaneous speed at a given point, like for this time t prime, I've taken this point and a very, very close point to it. So I've taken something like this, that the red dot represents the instant of time t prime, but the green dot represents an instant of time very, very close to the first one. It is t prime plus delta t. So this delta t is extremely small. So if I calculate the ratio of distance traveled upon time for this very, very short interval of time between two instants which are almost merging because delta t is extremely small, even then that rate will be the same as the average rate between t1 and t2. Why? Because we are moving at uniform speed. Why? Because there's no external force acting on the body. Like the example I gave you, a particle moving on a frictionless surface or a body moving on a frictionless surface with uniform speed. Okay. Now this is going to change drastically the moment there is acceleration involved. And that problem was basically the birth of calculus. Okay. So you can just go through this example also once more. Okay. Of course, this was more generic because some of you wanted to understand the concept of slope of straight line and the general equation of straight line. So this was aside from this. This was.
Excuse me, sir.
Yes.
Sir, are you going to send this PDF in our group?
Yes, I'm going to send it.
Okay, sir.
About
Thank you,
equation
sir.
of, yeah. Every lecture I'm going to send the PDF, so don't worry. Which is basically coordinate geometry. Okay. Now let us come to a situation where we are looking at distance versus time for a non-uniform motion. If we have a distance time graph, so now I'm giving you an example graph, and first of all, we'll make some observations about this example graph. Then we will come back to the whole business of average versus instantaneous speed. So suppose the distance, notice that I'm not talking about displacement and velocity yet. I'm just talking about scalar quantities, distance and speed. So supposing the distance time graph, which I have plotted according to the experimental data in some experiment. Okay, so I have, from the experimental data, I know that the distance after a certain time is so much, then at a different time it's so much. So I plot all those points, and from those points I plot this graph, which comes out to be, suppose it comes out to be like this. Okay, now what is the first thing I can observe about this? Can you tell me the observation? What I can make from this?
Non-linear.
Yeah, it's a non-linear graph, first of all.
Accelerated motion.
Rishabh, sorry, coming back to your question, just a moment. I had not seen this question. Rishabh, that motion of the rotating wheel in particular, it's called rolling. Okay, rolling is a type of motion when any point of contact does not slip on the ground. So in rolling situation, what happens? The distance traveled in one complete cycle is equal to 2 pi r. Okay, is it clear?
So that was clear. The wave formed by a singular point in that rolling motion. So you mentioned a name, I could not catch it.
Cycloidal motion.
All right.
That is the path of a single point on the circumference. It's called cycloidal motion. We'll be studying about it in detail, I think something like 4 or 5 months from now. Okay, but you can look it up. It's very interesting. Cycloidal motion. Okay. Yeah, anyway, yeah. So coming back to this graph, so I'm getting answers for the observations. Yes. So some of you, for example, have told me that first of all, it's a non-linear graph. Okay. So first observation I can see, it is non-linear. Okay. Okay. So what does non-linear basically mean in terms of speed? Can you tell me, if it's non-linear, what we can say about speed?
Non-uniform
changing.
speed.
Yes, it's changing. You know, it is. We can say that it is non-uniform speed.
Accelerated.
Or yeah, or it is changing speed. So first of all, we can see it is changing speed. Then we come to the point that you have just made. Okay, that it is accelerated, or the point that, okay, many of you made on the chat. Adinath, you have mentioned perf. You have mentioned okay, that if we look at the speed, not only it is changing, but what we can say about the slope, it is increasing. So that means what we can say about the instantaneous speed here, it is increasing. So notice that in the particular example that I have shown over here, we can see that the slope is not only changing, which is why it is non-linear, it is increasing. It has an increasing slope. So now this is very interesting. How can I define slope for a curve? So I'm coming to that. But that means basically that it has an increasing speed. Okay, which means that it is continuously accelerated. So it is what we call accelerated motion. In common everyday language, we call it accelerated motion. Okay. Now, how I know it is accelerated motion, how I know the speed is increasing? Let's try to understand this. Okay. So here, if I were to calculate the distance traveled in some interval of time like this, delta t, so this is delta s1, let's say, okay, because it's from time t1 to time t2. So I'm seeing that t2 is equal to t1 plus some delta t. Okay. Now, if I repeat that interval of time, but at a later instant, I mean, I repeat the same, but this is going from t3 to some t4, such that this interval is the same. Okay. But you can see that this distance is something different. This is now some delta s prime, let's say, okay, whereas this was some delta s. So I can see that the two intervals are same. T1 to T2 is the same interval as T3 to T4, but the distances traveled are not the same. That is what is showing me that it's non-linear motion. or it's non-uniform motion. Non-linear because it's not a straight line graph, okay, but non-uniform. Why? Because in equal intervals of time it is not covering equal distances. Okay, t4 is equal to t3 plus delta t. So how I know this fact that the motion is non-uniform or the speed is non-uniform? I know that because the distance traveled is not equal in equal intervals of time. But how I know that it is increasing? How I know it's having increasing speed? Because delta s prime is greater than delta s. Okay, so as time is progressing in the same intervals of time, it is traveling more and more distance. So I know that it is a continuously accelerated motion. Okay, non-linear, of course, it was just by observation that it is not a straight line graph. Okay, the graph is not a straight line. So the moment I know that the graph is not a straight line, I know that the motion is what type? It is not uniform, it is non-uniform, because it no longer has that property that if I calculate distance for delta t at different points of time, if delta t is same, the distances are not going to be the same. So that's how I know it's non-uniform. So that means a non-linear curve corresponds to non-uniform motion, and non-uniform motion corresponds to the situation where the speed is not remaining constant. Now, in this case, the shape of the graph is such that you can see that the speed is increasing. So we say it is an accelerated motion. Okay. Now, in this graph, how will I define instantaneous speed and average speed? That becomes an interesting thing. So let's redraw the graph and let's understand how we would interpret the quantity instantaneous speed and how we would interpret the quantity average speed. So distance versus time. Right. So our graph was like this. Now, if I have some instant of time t1 over here, and I have some instant of time t2 over here, so the corresponding value of s, s1 over here, and the corresponding value of s at t2 is s2. Now let's come to the definition of average speed. Average speed for the interval t1 to t2. So this average speed would be defined as the distance traveled divided by the time interval. So it would be s2 minus s1 upon t2 minus t1. Remember, average speed is always defined for an interval. Okay. So that's all fine. Given this graph, I should be able to calculate this. Okay. Given the graph and given time t1 and t2, I should be able to plot this line like this, calculate how much s1 and s2 is. Okay. But now you can see that this has a geometrical meaning. What is the geometrical meaning of this? Okay. So coming back here, if you just plot this forward, you can see that this quantity here is nothing but delta s. It is s2 minus s1, right? And this quantity in the graph is nothing but delta t. So it is nothing but t2 minus t1. Okay. So now, if I join these 2 points with a straight line, what does this delta s by delta t represent? It represents the slope, but it represents the slope of that straight line. If I just join these 2 points with a straight line, okay, then it represents tan theta for that straight line. See this ratio of delta s by delta t, what it represents? It represents this tan theta. Okay, so geometrical meaning of this average speed, now what it becomes, delta S by delta T is the slope of, now this type of a line is called a secant line. This is a new term we will learn. Okay. It is the slope of the secant line from T1 to T2. Average speed from T1 to T2 So we will do numerical examples of this also, but first I want to just understand the geometrical meaning, that if I'm defining average speed as total distance upon total time from some specific instant T1 to T2, and I'm given a graph like this, what is the geometrical meaning of that? It means that I have to join those 2 points on the graph with a straight line and do nothing but calculate the slope of that straight line. Okay. And that is why, you know, in the earlier graph, if you see, if you join these 2 points with a straight line, and then again you join these 2 points with a straight line, you can see that the slope is increasing. So that is what I meant by saying that the slope of the curve is increasing. It has an increasing slope. Okay. And that is why I could see that the speed is increasing. So it is a continuously accelerated motion. Okay. So this is the definition of average speed when it comes to a general type of motion. Okay. It is the slope of the secant line joining the 2 points for which I am calculating the average speed. Okay. So secant line is a straight line joining the 2 points on the S versus T graph at T equal to T1 and T equal to T2. That is the meaning of this. Okay. So that is how we define the average speed. Okay. So I'll just give you a moment to go through this and note down any key points that you want. Then we'll talk about instantaneous speed.
Sir, between
Yes.
the algebraic expression and geometric expression, there will be some difference, right?
Difference in the sense that
Means what the final answer we will get. Like here we are doing S2 minus S1 upon T2 minus T1, and here we are considering tan theta. So in the both the values there will be difference.
No, there won't be any difference, because see, like whatever algebraic expression we use now, S2 minus S1 is this vertical line.
Yes, sir.
You understanding? And T2 minus T1 is this horizontal distance.
Right, sir.
Okay. So for that purple colored line which I've drawn now, which is called the secant line. Okay, that is nothing but tan theta, na, delta S by delta T. इन दोनों का रेशियो ही तो tan theta होगा ना.
हाँ, but it is a straight line and we have drawn it. But the actual graph represents a curve structure.
Yeah, but even in the actual graph only, na, what do we mean by the average speed from T1 to T2? It's the same thing, na, delta S by delta T.
Yes, sir.
Okay, so that is what becomes the interesting point, na? Like if I'm seeing these 2 specific points on the S versus T graph, that at some T1 the distance was some S1, so this point has to be there on the graph. Okay, and at some time T2 the total distance from the origin was S2. Okay, so now any graph that passes through these 2 points, okay,
yes,
it could have
understood.
been understood the point. It could be a motion which went like this, it could be a motion which went like this, it could even be a motion that went like this, straight line motion. I mean uniform motion, but all three will have the same average speed between T1 and T2.
Right, sir. Yes, understood.
Because all three have the same secant line. So basically any curve which has the same secant line between T1 and T2 will correspond to the same average speed between the time T1 and T2. So that's actually an interesting thing that we've come across by observing your point, that actually the average speed between these two instants is independent of how the blue colored curve goes. It only depends on the secant line between those 2 points.
So in this example too, the average speed and the instantaneous speed is also equal.
No, I'm coming to instantaneous speed. Okay, in a moment I'm coming to that. So through this we will see that the moment we go outside the domain of straight line graph, okay, that is we are going to non-uniform motion, that definition goes away, that instantaneous speed is equal to average speed. So first of all, we can see in this example that average speed only is not remaining constant. You understanding the point? Average speed from T1 to T2 is not the same as average speed from T3 to T4, even though the time interval is the same. Okay, yes. So let alone the comparison between instantaneous and average. Even average is not the same if I take two different intervals. Okay, hope the point is clear, beta. Yes, come again, beta.
So can you repeat the point that you mentioned now?
So in this example, now you can see that the average speed from T1 to T2 is not equal to the average speed from T3 to T4. Even though the time interval is same, delta T is same between T1 and T2 and T3 and T4. So average speed in equal intervals of time is not remaining constant because it has an increasing slope.
Okay, sir.
So instantaneous speed, though we haven't talked about yet, but even if we look at average speed at different intervals of time between T1 and T2 and T3 and T4, even though the gap between them is same, T2 minus T1 is the same thing as T4 minus T3, but the average speed between T1 and T2 is not equal to the average speed between T3 and T4. Why? Because it's not a straight line anymore. And in this case, you can see that it's curving in such a way that the average speed in equal intervals of time goes on increasing as time increases.
Okay.
Okay. So this particular graph has that feature that if we look at the average speed for several equal intervals of time, equal in terms of the difference of time. Okay. So if I plot the average speed between T1, T2, then T2, T3, then T3, T4 like this, you can see that the slope of a line joining these 2 points is less than the slope of a line joining these 2 points, is less than the slope of a line joining these 2 points. So the slope between these lines is going on increasing. Okay, so average speed from T2 to T3 is greater than average speed from T1 to T2. Average speed from T3 to T4 is greater than the average speed from T2 to T3. Because you can see that if you join these 2 dots with a straight line compared to the other 2 dots, okay, the slope of such straight lines is going on increasing. As you go along this direction, the slope is increasing. It's going like this, then like this. So the slope is increasing all the time. That's because this particular graph is curving like this. It need not always be the case. Now let's come to instantaneous speed. Okay, so that is the whole subject of calculus, that how we will eventually deal with the problem of instantaneous speed. So this is speed at an instant. Okay, so it is delta s by delta t, but under the condition that delta t should be extremely small. Okay. So graphically, let's try to understand what that means. Now let us say that this is some particular instant of time. T naught. Now I want to calculate instantaneous speed p at the instant of time t equal to t naught. So how would I interpret this? Okay, let's try to understand that. So what I would have to do is I would have to get more and more accuracy, I would have to magnify this graph a lot. Okay. So this point here corresponds to t naught. So at that instant, the distance from the initial point is some s naught. Okay. Now I'd have to select a point which is extremely close to t naught. Okay. So close that this time interval delta t is extremely small. So this time here would be t naught plus delta t, where now this interval of time is extremely small. Okay. And that would correspond to a small distance traveled in that very small interval of time. So it's like the rotation of one wheel of the car which has happened during that very small interval of time. Okay. So now, as per the algebraic definition, B would be equal to delta S by delta T, which I've shown in the graph, where delta T is very small. Okay. But if you magnify this, so now if you magnify this point a lot, it would look something like this. So this is my delta T. This is my delta X. Okay. So now in this magnified diagram only, if I were to join these 2 points with a straight line, how that would look like? That straight line would look like this. So back in the graph, if I join these 2 points with a straight line and extend it, that straight line would look like this. So such a straight line is called a tangent line. Like you have a tangent to a circle drawn to a certain point. So like that, we have a tangent to any curve. In this case, that curve is representing the distance versus time. So geometrically, what does the meaning of this become? It is the slope of the tangent line. Okay. So what is the tangent line? The tangent line is a line joining the point at the instant t equal to t naught with another point extremely close to it. Okay. So that extremely close point is almost like the next consecutive point on the graph. It's like the distance between these 2 points is tending to 0. So if it is a next consecutive point, that means delta t tends to 0. Okay. This is what we are trying to do when we calculate the the instantaneous speed at that particular point. Given the graph of distance versus time, we want to calculate the instantaneous speed at a particular instant of time. What we'll have to do is, so I'll magnify this graph once more and show you first. Okay. So I'm given this graph of distance versus time. And what I want to do is I want to calculate the instantaneous speed at this time t naught. So what I'll have to do is I'll have to draw that point on the graph at time t naught and then draw the next consecutive point on the graph. Okay, so the distance between these 2 points should be extremely small. So what I mean by extremely small now is that delta t should be tending to 0. So that these two become like consecutive points on that curved line, on that curve of s versus t. So now these 2 consecutive points, if I join them with a straight line, that is called a tangent line. And the slope of that tangent is nothing but the instantaneous speed. So that is the geometrical interpretation of what I mean by instantaneous rate of change. It becomes the slope of the curve at the given point. Now, as you can see, it's not something so easy to calculate. Okay, so we have to define a whole new set of formulae and set of principles in mathematics, how we will calculate the slope of a tangent. It's not like a formula s2 minus s1 upon t2 minus t1. Okay, we have to develop a whole new thing in mathematics, and that is what is differential calculus. Okay, so just make a note of this and go through this. Let me know if there are any doubts. Yes, I'm coming to your doubt. Yeah, you can, that is correct to say, Siddharth, that it is actually like a secant line, but the difference between a secant line and a tangent line is a secant line joins 2 distinct points on a curve, whereas a tangent line joins 2 consecutive points. Okay, this diagram that I made below, it is just for demonstration purpose, but actually what is happening, the purple colored dot and the red colored dot, they should come on top of each other. They should be consecutive points. Okay, hope that's making the point a bit more clear. So when we are talking about the tangent between 2 points now on a curve, the tangent should be a line joining 1 point on the curve with the next particular consecutive point only. Then it is a perfect tangent. Okay, so if we manage to join 2 such points, then the tangent that we are drawing by extending that line joining those 2 points, consecutive points, that is nothing but the tangent line. Okay, so as you can see, it's easier said than done, and it's a little bit more difficult to actually construct than define. So that is where the science of calculus comes in, that how we will define how we will calculate the exact slope of the tangent using a new kind of mechanism, using a new mathematical machinery that is called calculus. Yes, so Anshul, your point is clear, is correct, that also in this case we can see that the instantaneous speed is changing from time to time. Every instant we have a different value of instantaneous speed, and that is why we call this which type of motion, non-uniform motion. Yes, Harshit, that is saying, that's correct, that we can say that the 2 points are then almost coinciding. Okay, so then if it's a next consecutive time point on the graph, that does mean that therefore t equal to t naught and t equal to t naught plus delta t on the graph almost coincide or overlap, because there are two consecutive points. Soham, I will answer that question. Okay, with time you will see that calculus is applied in all areas of physics and mathematics, not just distance and time. No. For example, electric current is the rate of flow of charge. Okay, force is the rate of change of momentum. Okay, we will see later that electric field is the gradient of potential. Okay, so that's also a type of slope. So wherever we are trying to understand the relationship between two physical quantities, and through that relationship we want to calculate the rate of change, okay, the science of differential calculus will come into play. And then of course there's a whole second branch of calculus called integral calculus, which will apply to the reverse of this. That is where we know the slope, how we can know the value of the function. So calculus is something very, very generic. Okay, in physics it's applied to almost any and everything, because physics after all is the study of the relationship between different physical quantities. So when we study the relationship between physical quantities, how they are affecting each other, naturally one part of that study will be the rate of change. So we want to understand how heat is varying with temperature, or density is varying, or mass is varying with density, etc. So we'll want to understand how the rate of change also works. What is the rate at which heat is supplied for a certain rate at which temperature is changing. So the moment we are talking about the concept of rate of change between two parameters, because one depends on the other, we are talking about differential calculus. It can go beyond physics also. Okay, for example, in economics, we want to study stock markets and what are the factors which affect the indexes of the various stock markets, or the pricing, or the base levels, etc. Again, we want to study the rate of change according to the different factors or the different parameters. So differential calculus becomes an important part of it. That is why you will see that generally people who are in finance from an engineering background are more successful in finance. I mean, generally speaking, it's not always the case, because they have a very strong background in calculus, which applies very well to finance also, finance and economics.
Isn't calculus in mathematics?
Yes, calculus is a branch of mathematics, but it is applied primarily to physics. Even vectors is a branch of mathematics, but it is applied primarily to physics. Okay. And without the understanding of the basics of calculus and vectors, we cannot understand the fundamentals of physics. That is why in this course we always start with vectors and calculus. When we have a bit of background with understanding of vectors and calculus, then we are in a position to start the actual understanding of physics. Okay, so this point is clear to all of you. Okay. Yeah, so Maitri, to bring your point forward, na, I'll explain about tangent of a circle also. Just give me an instant. So when we talk about tangent of a circle, na, it's actually the same thing. We draw a circle like this, okay, and then we draw the tangent to a circle from some external point. We are dropping the tangent, suppose. So let's say from some arbitrary point here, this is the tangent to the circle. So the tangent has like almost it's touching, it's gliding past the circle at a certain point E. Okay. So if we magnify the diagram at this point E, we magnify this, then what we'll come across is this actually. This is the circle. On the circle, if this point is A, then the tangent is going something like this. So it is as if it is joining that point A with the next consecutive point, the point which is so close to it that it's almost overlapping. You're understanding better? Just like, you can see that A and B are two dots which are one after the other on the circle. So they are almost merging. And the tangent is the one which is joining those two. Okay. Very good. So like that, if we have any general curve like this, and we want to draw a tangent at any particular point, we have to imagine that we are joining this. Okay. At this sort of a point, the tangent will be like this. At this sort of the point, the tangent might be like this. Now coming back to our generic example of non-uniform motion. Now suppose we had a situation where the distance versus time so suppose our distance versus time is now changing like this. Okay. What we can observe over here, what can be said about the instantaneous speed? Suppose I have the instantaneous speed at t1 here, I'm calculating that, and then again later at a different instant of time t2. This time what is different about this graph? Can anybody tell?
It's a deaccelerating.
Yes, it's a deaccelerating motion. You can see the instantaneous speed at t1 will correspond to this sort of a tangent line. Correspond to this sort of a tangent line. So this is the tangent at t equal to t1. And correspondingly, the tangent at t equal to t2 be like this, let's say. So you can see that v1 will be greater than v2. Okay. So it's a decelerated motion. Speed is decreasing continuously. In fact, even if we take average speed for equal intervals of time, even that will be decreasing. But the point over here is about instantaneous speed, it's decreasing. Okay. Now let's come to our first numerical example. Okay. Now that we have understood the meaning of average speed and instantaneous speed, okay, in terms of geometrical representation, it is secant line slope, which is the average speed, and tangent line slope, which is the instantaneous speed. Okay. So suppose we have a situation that a particle moves along the x-axis such that it covers a distance of s equal to, let's say, t square from time t equal to 0 to t equal to t. So first of all, we want to plot an approximate graph of s versus t. Here s is equal to t square mein s is in meters, okay, and t is in seconds. Then from that graph, what we want to do is we want to calculate the average speed from t equal to 0 to 2 seconds, and then t equal to 2 seconds to 4 seconds. And then third point, we want to find the instantaneous speed at t equal to 2 seconds. Exactly at t equal to 2 seconds, we want to calculate the instantaneous speed. Okay, just give this a try. I'll start working it out in a couple of minutes, but try it out yourself. Okay, so just continue with your solving. I will just start with the basic graph, how you try and plot it. So if you start taking a set of values, now you will realize why the graph will be like this. At t equal to 0, s is equal to 0. Okay. T equal to, let's say, 0.5 seconds, s would be 0.25 meters. Okay. Then t equal to 1 second, s would be 1 meter. Okay. T equal to 1.5 seconds, s would be 2.25 meters. T equal to 2 seconds, s would be 4 meters. T equal to 2.5 seconds, let's say, s would be 6.25 meters. Like this, if you go on plotting, for example, at 3 seconds, s is 9 meters. At 4 seconds, s is 16 meters, and so on and so forth. Okay. So if you plot this, making a set of ordered pairs and all that, and trying to join them with the smoothest possible curve, you will see you will get some curve which will go like this. Okay. Where, for example, this is 1 second, 1 meter. Okay. This is 2 seconds, 4 meters. You don't have to draw it exactly to scale and all that. You just have to make a rough estimate. If you draw it on graph paper exactly to scale, then it will be that much better, but it's not really required over here for us. And so on and so forth. Okay, this is what roughly the graph will look like. Okay, so now let's come to the first part. I want to calculate the average speed from, what was it, 0 to 2 seconds, right? 0 to 2 seconds, and then 2 to 4 seconds. So for the A part, I want to calculate average speed from 0 to 2 seconds. So that is distance traveled from 0 to 2 seconds divided by 2 seconds. Okay. So in terms of graph, what would that mean? That would mean the secant line joining these 2 points here. Joining the point on the graph at t equal to 0 with the point on the graph at t
So
equal
your
to 2
voice is
seconds.
not audible.
Yeah, the audio output is good from my end. Just maybe increase the volume or check your audio settings once. Okay. So I'd have to draw a secant line joining these 2 points. This is the point at t equal to 2 seconds. So this is the point B, and this is the origin point. So this would be basically the geometrical meaning would be the slope of the secant line let's say OB. Okay. So as you can see, the distance traveled is 4 meters in an interval of 2 seconds. So the average speed would be 2 meters per second. This would be the answer of the first part, of the A part of second part. Okay. Now like that, the second part I want to calculate the average speed from 2 to 4 seconds. So that would be what? That would be the distance traveled from 2 to 4 seconds divided by the time interval. So geometrically, what I would be doing in the second part, I would be joining this point B, which is at 2 seconds, with let's say this point C, which is at 4 seconds. So I'd be calculating the slope of this secant line now. I'd be calculating this tan theta. This is delta S from 2 to 4 seconds, which you can see is how much? It is 16 minus 4 or 12 meters. Okay. And this is delta T, which is 2 seconds. So it has increased to 6 meters per second. You can see the average speed is the two intervals are both 2 second intervals, but the first is from 0 to 2, the second is from 2 to 4. So the nature of this is such that, okay, so this is the secant line BC. So this is the slope of secant line BC. So this is clear so far?
Yes, sir.
Okay. Okay. I know you have a class coming up at 11 o'clock, but we'll just take another 2 to 3 minutes. Okay, now let's come to the, so this part is clear, I hope to all of you know. Now let's come to the third part. We want to calculate the instantaneous speed at t equal to 2 seconds. So this is where the whole thing of calculus will begin for us. So now what we want to do is exactly at this point, t equal to 2 seconds, we want to draw a tangent line. So it's, as I said, it's easier said than done, drawing a tangent line. Anyhow, so roughly speaking, this is, let's say, a tangent at t equal to 2 seconds. that is this point B. Okay. So once again, if we put this point under a magnifier, what we are trying to do is we are trying to achieve this, that we've taken the instant t equal to 2 seconds, and then we've taken the next consecutive point, so that our delta t is very small. So delta t is tending to 0. So this is the delta s during that time. Okay. And then we are joining these 2 points with the straight line, which is nothing but the tangent line. Okay. So now what we'll do is we'll do this calculation algebraically. We will calculate instantaneous speed as delta s by delta t, but with the condition that delta t should be tending to 0. So it should be very small. Okay. Now remember, the original equation for s was how much? S is equal to t square. Now somebody just suggest a small value of delta t. Just suggest what comes to mind. Yes, Rishabh, you have some doubt, beta? Yeah, Adinath, we can take 0.1 second, 0.01 second, that's correct. Yeah, Rishabh, you had some doubt?
Yes, sir, I've written it. All right, I'll just say it.
Yeah, it's fine. You can send my message also, it's fine. Yeah, so Adinath has suggested, let us take delta s, delta t equal to 0.01 seconds. Okay. Now, if we do that for this calculation, we should take t1 as 2.00 seconds, and we should take t2 as what? 2.01 seconds. Okay. So then what will be the value of s1? Okay. So that will be 4. Okay. And what will be the value of s2? It will be 2.01 square. Can you tell me how much this is? 2.01 square.
$40401.
Yeah. So 4.0401. No? Be like this. Okay. So if I take these values of T1 and T2, what is my V going to come out to be? It's going to be S2 minus S1 upon T2 minus T1, which is going to be 4.0401 minus 4 like this divided by this. So as you can see, how much is coming out to be? It's coming out to be 0.0401 divided by 0.01 in meters per second. So it's coming out to be 0.01 meters per second. So this is the value of instantaneous speed I'm getting, but it has a limitation on accuracy. The limitation on accuracy is that I've taken delta t to be 0.01 seconds. Right. I've taken delta t to be 0.01 seconds. Now let's take a case where I go even more accurate. Okay. Suppose I take delta t next.
Sir,
Yes.
so the velocity will be 0.401.
No, beta. It's 0.0401 divided by 0.01. No? Understood? No? See the numerator numerator, it's 4.01 into 10 raised per minus 2. No? And the denominator is how much? 1 into 10 raised per minus 2.
Achha.
What it? Achha, now let's take the second case where I take delta t as even bit more accurate. So I take it as 1 millisecond. Instead of 10 milliseconds, I take it as 1 millisecond. This one was 10 milliseconds. So I'm a little bit more accurate. Okay. So in this case, T2 being 2.001 seconds, you will see S2 will become 2.001 square, which will actually give you 4.040001. Sorry, be 1 less 0. Okay, so this time if I check my instantaneous speed, which is delta S by delta T,
Or 2.001 square is 4.004.
just a second, this will be slightly different. Yeah, 2.001 seconds whole square will give me how much? It will give me 4.004001. This is the point you were making, Beta?
Yes, sir.
Yeah. So this numerator will become 0.004001. So this time how much we are getting? We are getting it as 4.001 meters per second. So you can see that these are almost the same, but this is closer to 4 than this is. So when I'm increasing my level of accuracy, I'm getting a number which is even closer to 4 compared to this. Okay. So I can say that this is almost equal to 4. This is also almost equal to 4, but this is more accurate. Compared to this, because the interval of time that I've taken is even less. So through this natural progression, you can understand that the smaller the value of delta t I take, the closer the value will come to 4. Just by a method of extrapolating this, okay, that when I'd taken it as 0.01, it was accurate up to first place of decimal. It was equal to 4 if I approximate up to first place of decimal. If I take 0.001, it will be equal to 4 exactly, even if I approximate up to second place of decimal. So like that, suppose I had taken, instead of 1 millisecond, I had taken 1 nanosecond or 1 femtosecond or something very, very small like that, then it would be even that much closer to 4. Okay. So this point can ultimately be proved algebraically. If we do a calculation like this, that we calculate V is equal to delta S by delta T, but by taking delta T tending to 0. So it's so small that it's actually tending to 0. Okay. So in this case, we would take T1 as 2 seconds. So we take S1 as 4 meters, but we take T2 as 2 plus delta T seconds. So we'll take S2 as 2 plus delta T whole square in meters, with the condition, of course, that delta T is extremely small, it's tending to 0. So now let's see what we are getting from here.
Sir, S2 will be 2 plus 4 delta. No, right.
This only, na? When we expand it, you will get that. Okay. What you're saying we'll get when we expand this. Okay. So 2 plus delta t को whole square कर देंगे minus 2 square here divided by delta t. Correct. But with the condition that delta t is tending to 0. Okay. So what does the numerator now become? It becomes 2 delta t plus delta t square. But with the condition that delta t is very small. Okay. So this step is clear now. We are just expanding this. So next step you can see that we can take delta t common in the numerator. So it becomes 2 plus delta t divided by delta t. Okay. Now what we can do is we can cancel this. Now the reason why we can cancel this is, remember, delta t is not 0. It is tending to 0. Okay. Delta t tends to 0, but is not equal to 0. If it were equal to 0, we cannot cancel because 0 by 0 is not defined. Okay, so delta t is not equal to 0. So this cancellation is fine. There's no problem with it. So what we are left with? We are left with 2 plus delta t, with delta t being very small.
Sir, where we have expand, I think there is something error.
Yeah, it should be 4. It should be 4 delta t. Okay. It's correct. Just make this correction here. It should be 4 delta t. Okay. Because just use this. This is 2 square plus this. Basically using the formula. Like this. Okay. All right. So this is ultimately becoming how much? This is becoming 4 plus delta t, but with the condition that delta t is so small that it's tending to 0. So what it should be equal to? It should be 4. So this is the proof that the instantaneous speed at that time is in fact equal to 4. Okay, so what this is showing us is that the instantaneous speed will have an exact value of 4 meters per second at the instant t equal to 2 seconds. Okay, for s is equal to t square. Okay, so hope this is clear to all of you.
Yes, sir.
Okay. Achha, by the way, anybody has another approach to this? How we can come from this conclusion to this conclusion? Okay. S is equal to ut plus half at square. When that happens, when a is constant. So if you compare this with s is equal to t square, how much is your u? It's 0. And how much is your a? It's 2 meters per second square. So in that case, what should your v be? V should be equal to u plus at. So in this case, how much will be your v? It will be 2t. So at t equal to 2 seconds, how much it should be? It should be 4 meters per second.
Yes, sir.
Okay. So what we'll actually show later, that these equations, that s is equal to ut plus half at square, v is equal to u plus at, because acceleration is constant, these have actually come from calculus. Okay, the derivation of these equations actually comes from calculus. Okay, people. So anyhow, hope you understood this particular example of instantaneous speed today. Okay.
Yes.
Now we will, yeah. So we will expand on this concept further with differential calculus next time. So we will see that we can develop. Yeah, Parv, you have a question?
Yes, sir.
Yes.
How did we take the acceleration as 2 meters per second square?
How we took this? So see, this is the standard equation that s is equal to ut plus half at square in the case when acceleration is constant, for constant or uniform acceleration. Okay. Now the particular equation that we have is what? That s is equal to t square. So if you compare these two equations now, on comparison, what is the coefficient of t? The coefficient of t is u, but is there any coefficient of t here? No, it's 0. Okay. Then what is the coefficient of t square here? It is half a. So what is the coefficient of t square over here? It's 1. Okay. And t is in second, s is in meters. So that means a is equal to how much? 2 meters per second square. Right? Understood now?
Yes.
Okay. So that's the alternate way. But then that's the formula based way. And what we have to understand is that the formula has actually come from calculus. Yes, Zarar, you have a question, beta?
Sir, can you explain the last statement that you've written in the note that
as t tends to 0? Okay. So t tends to 0 means it's not equal to 0. No, it's something very, very small. It might be 10 raised by minus 5. It might be 10 raised by minus 50 also. But it's not exactly equal to 0. No, it's almost equal to 0, but not equal to 0. Is the point clear, Zara?
yes, sir?
Okay. And that is why we are able to cancel the delta t numerator denominator, because I'm sure that it is not equal to 0. It's very small, but it's not equal to 0, because if there's a possibility that delta t is 0, then we cannot cancel like this, because 0 by 0 is not defined in maths. 0 by 0 is not 1, but 10 raised by minus 15 divided by 10 raised by minus 15 is still equal to 1. So that's a technical point in maths. Hope it's clear, Zara.
Yes, sir.
Okay. So with this, we conclude today's session. And as I said, next time we will be discussing in more depth about this process of instantaneous rate of change using differential calculus. So we'll see if we have a more complicated formula also of distance versus time, like distance might depend on cubic function or square root function, anything like that, how we will calculate the instantaneous rate of change. Yes, Soham, you should use a different notebook for each and every different track of your syllabus. So for chemistry, you will require 2 notebooks, for physics 2 notebooks, and for maths 2 notebooks. Your next lecture is going to be mole concept, so make a separate notebook for that, please. Okay, so that's it for today's session, people. I will send you the recording and the notes. Okay, so please go through that carefully, and I'll also send you a small little worksheet of questions just to revise the concepts that we've learned today. Okay.
Thank you, sir.
Okay, people, that's it. Goodbye. Take care.
Bye, sir. Thank you.
Thank you, sir.
So 3 topics will go on at the same time.
Yeah, this same topic will continue in the next lecture. Yes.
Thank you, sir.